So last lecture we talked about some of the basic ideas and principles of how to move your startup along faster and more efficiently. And today we're going to talk about the technical things you can do to help move your startup along. But first I wanted to deal with an issue that's probably been on all your minds. The question you've wanted to ask me, and that's, Dr. Cho, what the heck is up with the hair? Well, I'm not a young man. And so I reached the stage of the midlife crisis. And so what do guys do? Did I want to buy a fast car? Well, if I had a fast car, I'd be dead in a month because I have a tendency to push things. This is why I don't own a motorcycle. Do I want to chase young girls? Nah, I have no interest in doing that. I, quite frankly, have never understood it. Because what do you talk about? You're from like totally different generations. So I started thinking about what did I want to do. And then I remembered a boss I had. And when he was 40, he started going bald. And he said to me, I grew up as a kid with crew cuts. If I knew I was going to lose my hair so soon, I would have grown it out and had time to enjoy it. So I thought, what the heck? I might as well enjoy my hair while I can. And actually, I use it for more than just vanity or having fun. I actually donate it. Twice I've donated ponytails about this length. My hair gets down to about my tailbone, and I donate it towards cancer research. They take the hair and they turn it into wigs. So there's something productive out of it. So that's what's up with the hair. I think I can only do this one more time because the gray is starting to creep in. Anyway, today we're going to talk about the mechanics. And the mechanics are 3 different parts. And so these are the things that can help you execute more quickly. The first thing when you think about execution, the first thing you should be thinking about is the project management mindset. Project management is driven by what's called the triple constraint. How much time is it going to take? What resources do I have to put to the problem? And what is it that I'm going to deliver? And if I don't have enough of all 3, then what suffers is quality. You make hard decisions, you make trade-offs against the 3. You think about how much am I risking for how much am I going to get back. This was my huge advantage as an engineer. Other engineers come in and they're talking about flexural rigidity or weight or things like that, basically engineering variables. When I looked at an engineering problem, I also looked at the triple constraint because this is about execution. As we used to say, and you know it drives Dr. Cho crazy, today we're going to talk about learning quicker. Mindsets matter. Remember the guy in autopilot and he hopped in the back? And that's part of the problem in entrepreneurship. They throw around so many buzzwords, you get into a mindset. And nobody actually really understands what this really means or where it actually came from. And how do these mindsets sink in? It's because people are mentally lazy. We don't use rigor. Resources matter. You don't get an infinite number of times you can try something. And so what I'm trying to do is build within you, be smart from the beginning. Look at the entirety of it. Look at the complexity of it and appreciate what it is. Now, professors, what do they focus on? They're going to focus on your fear. We want you to try things. The problem is that when you create a mentality of, go ahead and try it, there's no penalty. Well, the problem is later on, when are you going to teach you about responsibility? Why not teach it from the beginning? Why dummy it down for you? So the mechanics. First, before you can get into mechanics, you need to understand what are objectives and goals. And they can't be done separately, they're tied together. In terms of metrics, we rely on what we know. But does it make sense? We value things because we're biased. But we're biased towards what we valued. You have to be aware of that. And not only that, but those biases, do you allow other people to take responsibility and have a role in what's going on? How good a leader are you? Why are goals such a powerful thing? Well, one, it's about productivity. It focuses our energy and attention. Goals are expression of how effective we can really be, and that's why we make these goals, because we believe they're attainable. And the one big thing about goals is, do you get feedback? There has to be some process, and the process says is once I get something, I feed it back, and that feedback can impact what I do next time. Goals are basically about processes. It gives us control over outcomes. Your process goals become your battle plan, and it decomposes into outcome process and learning goals. It's the beginning of strategy. Outcome goals are desired results. They're symptoms and causes. Here's where people get goals wrong. There's a difference between a goal and an objective. For example, we want to have this much return on our money or something like that. That's not a goal, that's an outcome. And it's an objective. Profitability is a feedback that you get to see how well your processes are working. Failure is not an event, it's a process. That's the way you need to look at it. That's the way you get around the fear factor of trying. Process, again, is about luck and skill. Focus on doing what's right. The thing about these kind of goals is scale matters. The larger the goal, the less control we have over it. And remember, it's about skill and luck. If you make goals too large, then it's more about luck than it is about skill. And that's why we make goals smaller. In terms of learning, what kind of goals do we want? We want information. We want new competencies, new ways of doing things. We want new strategies. And we want to supplement what we already do. Those are the things that happen in learning. For example, do your best. What the heck does that mean? Strong goals are easy to explain, but have a layer of complexity underneath them. Specificity. If you make things too specific, you miss goals. And so link it to an outcome, process, or learning. Is it measurable? Is it achievable? And is it relevant? Goals need to be smart. So goal setting as a strategy is you need sub-goals. You work backwards, and that's, you know what the outcome is. So how are you going to get there? There are things that are close up and there are things that are further away. The problem is that the things that are closer up skews the importance of them. So be aware of that. And what is the urgency involved? And this is where time and bias sets in. We want to create momentum, and momentum comes from velocity. Feedback is what propels you forward. And what that information does, it builds belief. And it builds a belief that we can succeed. In terms of dealing with failure, you need contingencies. What if something goes wrong? What is failure and what is learning? Do you understand what the difference between those are? And failure is a form of feedback. And what is failure? Failure is when information obtained can't be used to propel you forward. That's when it's failure. That's how you tell if it's failure or learning. So now we can get into the mechanics. And the mechanics are, how do you solve a big problem? Make it smaller. And history can, this is a case of where it's not about sunk costs, but historical data could be part of your learning. Here's one of my dirty secrets. I gained a reputation as a turnaround guy. I would come into situations where yield is 1% or less, and then when I leave, yield is 95%. I make processes that basically are extremely consistent. And I would do it very quickly. And then everybody would say, wow, that guy's really smart. And it's like, here's how I figured it out. First thing I would do is look at all the data that already exists. They had the answer. They just didn't see it. How flexible are your goals? How negotiable are they? And this is what sets your limits. Remember we talked about the boundaries? And also, how do we change scale? And so what happens is when you have a big problem, you have to make it smaller. Your experiments should always yield data. When you try something, if it doesn't work, what does that tell you? And this is why grad students take such a long time to graduate. They make bad experiments. When I made experiments, if it didn't work, it's like, okay, that's not too bad because I got learning. I learned that, no, this isn't going to work anymore. So when you start off with, you have this infinitely big problem. And somewhere along the line, you're going to have to set limits. Like, for example, we can't sell this more for $40. Then all of a sudden, all the possibilities above 40 disappear. And then when you learn something, you get another boundary, and another boundary, and another boundary. And what ends up happening is your problem is actually that size, not the whole enchilada. Where do these boundaries come from? What is the nature of the problem that I'm dealing with? That focuses me on the variables I need to look at. Am I being objective? And also, what requirements are there? So, what is it that I'm trying to figure out? Am I trying to see whether this is feasible? Do I want to validate something, or do I want to verify something? A big aspect of everything that you do as a startup revolves around time. And so in terms of experimenting, you have to also focus on time. And it's actually a very simple idea. Time, how much does it take me to do one cycle, to do one experiment? And how do I make that go faster? And how many tries do I think I'm going to need? Can I do it in fewer iterations? And that's what time is, the period times the number of cycles. So in terms of improving performance, I need to find ways to shorten cycles or reduce the number of cycles or do both. I need to look at the nature of what it is I'm doing and see what is it that I can actually impact. When you look at a problem, the first thing you should look at is it series or parallel. When tasks are in series, it means that you cannot do one thing until you did something else. For example, entering a room. If the door is closed, guess what? Somewhere along the line, you're going to have to open that door before you can get into the room. And you can think of serial things as being a chain. You just need one thing to fail and the entire chain fails. Make sure each step works first before you go on to the next link in the chain. The other thing I always liked about this is parallel. Parallel means that nothing is related to what you're doing. If nothing's related, that means I could do everything at the same time. This is where spending money or getting more people or getting more help really pays off, because everybody's working at the same time. Now, process development. A lot of people aren't very good at it. And part of it is their approach to doing experimentation. And this was my approach to do it from day one when I started doing process development, is I took time out and thought about it. And what people would do is semiconductor processes are very long. I mean, you could be talking about like 100 steps. And so what people would do is they would take a process all the way up to like step 50. Oh, it fails. Go back to step 1. Uh-oh, this time you failed on step 40. Go back to the beginning. Move forward. Go back and move forward. Go back and always back to step 1. And as you can see, this is incredibly time-consuming, but also very expensive. So what I would do is I would break the problem up into its primary steps. Each of these is what's referred to as orthogonal. And orthogonal means that they're independent. If there's no cross-dependencies between these steps. If everything is orthogonal, then what you can do is you can work on everything at the same time. And what I would do is, okay, step 1, the yield has got to be better than 99%. Step 2, the yield's got to be better than 99%. And so all these steps, I would work on these first. And everybody would be asking me, when are we going to get devices out? And I said, wait, we need to get the process down first. And it would just drive people crazy. It's like, what are you doing? Just run parts through. It doesn't work. And again, it's because it's a chain. I'll put it this way, if you only have 3 steps and it's 50% on each, 50% times 50% times 50%, now I only have a 12.5% chance of making it through. Part of the reason why they have 1% processes is they never fix the individual steps. So that's the first thing I do. The next step is, okay, I'll move like 100 wafers, and I'll do it through step 1. And then what'll happen is, if I'm sure that everything will yield and then that's a good process, I'll leave 25 behind and then move the next 75 over into step 2. And then if it doesn't work on step 2, then how long is it going to take me? Well, I've got 25 wafers at step 1. So I just keep working on it until step 2. I can go from step 1 to step 2. And then, actually, that's when I move my 75 wafers over. Then same thing with step 3. While I'm doing step 3, if something doesn't work, what is a regular process engineer going to do? All the way back to step 1. Here's the thing, when I moved on to step 2, I left 25 wafers behind. And so if step 3 didn't work, then I just go back to step 2, use those assets, and then keep going in circles until it worked. And what I would do is drop wafers at every step, so I don't have to come all the way back to the beginning. I could do fast loop testing. Here's the other thing about series elements. You have to do it in order. It's an onion. And the problem is that layers can hide layers. For example, you could have a problem, let's say layer 3 of this onion is rotten. However, you tell everybody this onion is great, there's no problem with it. And the reason why is because you can only see the onion from the outer layer. You don't know what's going on in the inner layer, and you can't conclude anything. And this is why you need to do things in steps. An example is IT. For any of you who've ever had to do with IT, it can be a bit insulting. Because what's the first thing they ask you? Is your computer plugged in? Have you logged on? And why do they do this? They're going through the onion. If your computer's not plugged in and if it's not turned on, then everything else they're going to ask you becomes irrelevant. You don't have to worry about the BIOS system problems you're having because your computer isn't on. And so, yes, it's insulting, but that's what they're doing. They're working through the onion to figure out where the problem actually exists. And here's a problem that illustrates the onion. So vacuum sealing. Vacuum sealed vessels that we made, these flat panel displays, they were leaking over a month. And so the physicists who were in our organization said it was outgassing. And what happens, and this happens to everything in a vacuum seal, you can never get the surfaces perfectly clean. So now that I have this vacuum, I have this void, nature doesn't like a void, what's going to happen? Stuff off the surface is going to come off that surface over time. And so all these molecules enter my vacuum and wreck my vacuum. And this is called outgassing. As you can imagine, as temperature goes up, your outgassing gets worse. But anyway, all these physicists were saying, oh, since it's leaking over a month, it's got to be outgassing. And so they started proposing all these experiments that would take 2 months. And this violates the onion. What's the outer layer here? The seal. If the seal is not sealed, then these guys are going to be chasing experiments onto forever because this thing is going to constantly be failing. And so what do? We looked at the seal and found out it had micro leaks. We had that seal fixed in 2 days, and outgassing turned out not to be a problem. Outgassing could still be a problem, but the point is, we've removed this from consideration. Now we can move on to the next layer of the onion. So we started out talking about variable reduction, our basic strategy of attacking problems. And we talked about the techniques of how you basically do variable reduction and everything else and execute more efficiently with regards to time. But somebody's got to execute it. The thing is, not everybody. People have very many different personalities. Not everybody is cut out to deal with uncertainty. However, I find that these are the kind of people that you want. You want throat cutters. not cutthroats. Cutthroats are people who stab you in the back. I mean people who get problems done, and when they solve problems, it doesn't become a problem again. There's a lot of people who look busy. There are very few people who actually get things done. I learned that from my first boss, and that was a piece of advice he gave me. You're not looking for cutthroats, but you're looking for throat cutters. In PhD programs, they call research the dragon, the big unknown. When you get the dragon down, cut its throat. If you don't, then it's going to take you for a ride. You think you have a solution, and then it's not a solution because it'll fail, and then you're going to have to keep fighting the same battle over and over and over again. Make sure you have it down. You're going to need heavy lifters. You need people who can execute. The flat panel display startup I worked with had 20 PhDs out of 100 employees. And I could hire someone from my department. And they wanted me to hire this PhD from Stanford. And I said, no. And they asked me, what do you mean no? And I said, I don't need another PhD to come in here and tell us what we're doing wrong. What I need right now is somebody who's going to get things moving and get things done. So I hired a heavy lifter. Nobody knows the answer. People who say they know the answer, then what's the point of doing everything if they're correct? Odds are they're probably wrong. You need people who are resourceful, not people who can find the answer. You need people who can go find answers, not people who think they know what the answer is. And actually, when I hired this gal, I asked her a question in the interview. She didn't know how to solve it, but then she told me, but here's how I would solve it. Now, I don't remember this, but if you go to this book, then they talk about it in there, and then I would go talk to this person, and then I would. And so they told me the process I would go through, and it was reasonable. They were resourceful. You need people who are realists. You need people who come to grips with the reality of the situation. And the reason why is when people have biases, they're believing they're the biases, not what you're actually dealing with. For example, and this happened to me in an interview, they asked me, are you a glass is half full or a guy where the glass is half empty? And I said, neither. They're like, what? And I said, I deal with the reality of the situation. I believe that glass has 4 ounces of water in it. And these are the kinds of people you need, the people who will deal with the reality of the situation because they're best aligned to actually solve the problem. Instead of coming out all over here, they're right here. Oh, by the way, in that interview, the guy paused and he sat back in his chair. And I said, is everything okay? And he said, I need a minute. You just blew my mind. Nobody's ever answered that question that way. So if you want to use that, feel free to. And that brings us into the mechanics. And now, we now go into the breach.